Hey, I hope that everybody's doing well. And I hope that you did well in the last test. So now we're hitting our last chapter of material. And before we jump back into chapter 5, which is where we're heading next, we have to pick up a few details or fundamentals from chapter 1 that we skipped over, okay? So what we're going to look at today is exponents and scientific notation. Mainly exponents, but a little bit of scientific notation too, okay? So before we get started, we're going to look at all the exponent rules, but before we dive too deeply into that, I do have a kind of bigger question is, what is an exponent? Does anybody know what an exponent is? What an exponent is it something that is counting how many multiplications we have. So this number right here up top is considered the exponent. My sloppy 5. I should try to draw it a little bit neater. So this is the exponent, x to the 5th. And this is called the base. So let's label these things. This is the exponent. The thing that the exponent is raised to is called the base. Okay. And what an exponent is doing is it's just a count of how many things are being multiplied. 1, 2, 3, 4. How many times this base is being multiplied by itself. So if I have x to the 5th, that means I have 5 x's being multiplied. Or if I wanted to go really simple, let's do a base that's a number so we can actually figure this out. Let's say 2 to the 3rd. Well, that would just be 1, 2, 3. And so then I know 2 times 2 is 4, right? And 4 times 2 is 8. Or you could just go 2 times 2 times 2 in your calculator and you'll see that's 8. But that's all an exponent is it's counting how many of the bases I have multiplied out. Okay? So this is built off of just multiplication. Now, we don't want to have to list out all these x's every time to figure out how to manipulate these or how to make them prettier. So we're going to dive into some exponent rules, and in no particular order. These are kind of I named some of these myself. I guess they don't all need names, but let's hit the first one. That's kind of the most important thing to know. And I'm going to write it kind of funny, but if you take anything, so I'm literally going to take anything, and if you raise it to the 0th power, that's going to equal 1. Okay? So, I mean, I could ask some simple questions like, oh, what is 4 to the 0th power? And you should tell me that is 1. I could do a pretty one. Or I could say, okay, how about negative 3 to the 0th power? Not a trick question. The answer is 1. I could do even trickier stuff like 2.057 plus x times pi divided by the square root of 3, and all in parentheses, and raise it to the 0th power. It does not matter. I know that anything raised to the 0th power is 1. Okay? Now, I can explain why this is true after I teach you a few more rules. I can kind of do a mock-up proof of why anything to the 0th power is 1. But we need more exponent rules, okay? So that's our first exponent rule. Anything to the 0th power, anything at all to the 0th power, is equal to 1. Okay? My 0 looks funny there, but... Alright, so before we move on to our next rule, I just want to tell you to be careful with something, okay? Just kind of be really cautious, or be careful with parentheses. Okay, parentheses, because there's a big difference in negative 5 squared versus parentheses negative 5 and the square on the outside of the parentheses, okay? You'll see these two, they're very different. If you just type them in your calculator as you see them, it depends on your calculator. This one's going to be tricky for some calculators. So we need to understand the difference in these two, because just grabbing our calculator might be misleading. Okay? So first off, let's look at this one. The rule is the exponent, it applies to what it is touching, to what it's touching. Okay, so look at this one. The 2 is right beside or touching the 5. It is not touching the negative. Y'all see that? So this one, while we lazily say this, we often mean this one over here. This one, this negative, is actually just going to be floating out front, and the 2, the exponent, is applied to the 5. That would be 5 times 5, right? And we know 5 times 5 is 25. Okay, so remember, the exponent just counts how many 5s I have. It is not counting the number of negatives because it's not touching the negative. The 2 is right beside the 5, not the negative. So the negative is literally floating out front, and it just gets brought down. Over here, it's very different. What is the 2 touching? Well, it's not touching the 5 or the negative. It's touching a parenthesis. Do y'all see that? It's touching a parenthesis. Well, what's a parenthesis? Remember, parenthesis is a grouping symbol. And so it has this entire term grouped. So what am I going to write out twice? I'm going to write out the parentheses twice. But whatever is inside the parentheses is grouped and has to come along for the ride. And so parentheses negative 5, square on the outside, means negative 5 times negative 5. And a negative times a negative is a positive. Remember, ugly daddy, ugly mama, pretty baby? And that makes it 25. So there's a difference. This one comes out with a negative 25. This one comes out positive. Lazily, we often mean parentheses without saying it or writing it. We're really guilty of this, especially in English. Okay, so just a caution. Another one that's very similar to this is, what if I used zeros? So very, very similar to that. The difference in negative 3 with parentheses to the 0th power versus negative 3 without parentheses. What's the 0 applying to here? The entire thing. Anything to the 0th power is just 1, right? Here, what is the 0 touching? It's not touching the negative. The negative is just going to float out front. The 0 is touching the 3. 3 to the 0th power is 1, right? So already notice that if the negative is inside the parentheses, we're going to get a positive. If the negative is outside the parentheses, or there are no parentheses here, with some of these I'm going to need to be careful, or I'm going to get a negative. Okay? Same thing that we just did. All right? So let's look at more rules. Okay? So this one is for when we are multiplying like bases. Multiplying like bases. Okay, now remember, the bases are the bottom numbers, right? So let me give you an example. If I have x squared times x to the 4th, there is a rule that tells us how to simplify this, okay? How to make this nicer. Let me give you the rule, and then I will explain why this rule is, and it's easy to see. The rule tells us to add the exponents together. So the goal, whenever I'm simplifying these things, is if I have the same base, is to compress same bases into 1. So x squared times x to the 4th, the rule tells you I can call that x to the 2 plus 4. Okay? Now, we all know 2 plus 4 is 6. So I can take two bases. These are two separate bases, but they are both x's. They have to be the same. And I'm allowed to say, oh, I have two x's here. I can smush them together into a single exponent term. How do I combine their exponents? If I am multiplying the bases, I add the exponents. 2 plus 4 is 6. Now, that is the rule. Let me show you where the rule comes from. Okay, so it's kind of some explanation, explaining why this rule works. Well, and you should always ask why. If you have any inkling of confusion, asking why is something you should always ask, and your math teacher should be good enough to explain why. If they don't, then they're not being nice. So, look at this. X squared, that's the same thing as, well, let me go ahead and write the problem over again first. x squared is the same thing as x times x, 2x's, right? And it's going to be times x to the fourth. Well, what's x to the fourth? That's the same thing as 4x's. 1, 2, 3, 4. I had to concentrate there. And then you look at this, and how many x's do I have multiplied together total? I have 2 plus 1, 2, 3, 4. I have 6 x's total. So if I want to write that way more neatly, I can just call that x to the sixth. So the idea is, instead of taking the time to write them all out, you know you're just going to count them all up in a second. This one is 2x's, this one's 4x's. That gives me a total of 6x's. Okay. I can expand this, so I can do more than just 2. I could do x to the second power times x to the third power times x to the, it does not matter, fifth power, something like that. And you could say, okay, well, I know that this is going to be x to the, if I'm trying to show my work here, 2 plus 3 plus 5, which is what, x to the 10? Those are 10 x's there, right? X to the 10. 10 x's being multiplied. Now, the part to focus on is that this only works for like bases, okay? So, for instance, if I have, look at this example, x to the third times y to the fourth, I cannot do anything with these because they are not the same base. I cannot smush them into a single base. This is just it. It's done. There's nothing I could simplify this with, okay? They have to be the same base. They could be numbers, you know, it could be 2 to the 15th times 2 to the 27th. And I could even add another one, times 5 to the 100. These are like bases, so I can combine those, right? 2 and 2, I would need to add their exponents. 2 to the 15 plus 27. And the 5 to the 100 is not the same base, so I cannot combine it. Now, I don't know if I said plus. 15 plus 27. It looks like I put a multiplication symbol there. Now, what is 15 plus 27? That'll be 2 to the 42 times 5 to the 100. And I do not want to see how big that number is. Just practicing the combining rules. Okay? That's good enough for an answer for right now. Okay? I do want to do one more of these with one that they love to do on the test. They love to do this. X times x to the third times x to the 7. And say, what is that? And so then you're looking at it and you say, 3 plus 7. But what about this guy floating out here? He's an x too. If I were to expand these out, that would be 1x, 1, 2, 3. So 1 and 3 makes 4 plus 7. That would make 11 x's. But people tend to forget single little guys like this. If there's not an exponent there, it's understood to be a 1. The reason it's understood to be a 1 is it's telling you how many x's I have. Well, definitely, x is just 1x, isn't it? So if there's ever an exponent that does not have, or base that does not have an exponent, you can give it a 1 if it helps you more easily follow your rules so that you don't forget to add it in when you combine all the like bases. And that is 11. Okay? So we've dealt with combining like bases. There's another one we need to deal with now. And what this one is, we would really like to not have any negative exponents. So how do we handle negative exponents? Alright, now let's talk about this one for a second. So negative exponents are okay, except for we don't want them in your final answers. This is not considered proper, and so you'll get the test, and it'll, if it doesn't, it should include on all the instructions to answer give your answers as simplified as possible with all positive exponents. This is considered improper. And so there's a way we fix it. If I have a base with negative exponents, trying to think the best way to do what the best first example would be here. Let's just start with this one. If I have a base with a negative exponent, there is a simple way we fix this, okay? So you see I have y to the negative fourth. The way to fix this is, if you have a negative base and exponent, we move it either up or down. In a fraction. So either move it if it's in the numerator to the denominator, or if it's in the denominator to the numerator. So you can kind of think of the negative sign in front of the exponent as like a light bulb. And what we're going to do is just move this switch from the up position, because this is understood to be on top of the fraction, isn't it? I could always put a 1 on the bottom to make this a fraction. And we see that y to the negative fourth is on top. So the way we fix this is to take anything that has a base with a negative exponent, move the base and its exponent to the opposite side. If it's up top, we move it to the bottom. If it's on the bottom, we move it up top. So this is on top. So I'm going to move y to the fourth to the bottom. And what that does, it's like a light switch. You can flip it up and down, up and down, up and down. And as you move it up and down, it just changes the sign of the exponent. So you see here the light's on, so we flip it down, the light is off. The light bulb is the negative sign. Now I can't leave it like this with a naked top. When we're dealing with fractions like these, this is the same sign that you see on the door at restaurants. No shoes, no shirt, no service. They never say anything about pants. So like y to the negative fourth, we didn't have to put a 1 on the bottom because you don't have to wear pants. But you got to put a shirt on it if there's nothing left up top. Okay. So there, got to put a 1 up top. Okay, no shoes, no shirt, no service. You got to have a shirt on. So let me give you another one to fix. How about one like this? 2 over x to the negative 5. Oh, it's hard to see my negative. Let me try making that a little bit neater. So 2 over x to the negative 5. So you look at this and you say, I'm not allowed a negative exponent. So this is in the bottom of the fraction, so it's going to move to the top. Okay, so this x to the negative 5 will move to the top and become x to the positive 5. What happens to the 2? Well, it actually does not move, because does it have a negative exponent? No, it has a positive exponent of 1, which I don't need to put. It's just a 2. It does not need to move. So now there's nothing left in my denominator. I don't have to do anything with my denominator. Notice once I flipped this up, or moved this up like the light switch, the lights went out. The light bulb is now off. And you could just move stuff up and down, and moving the base and the exponent up or down changes the sign of the exponent. So I move the x to the fifth up to the top, and now it's x to the negative fifth up to the top. Now it's positive x to the positive fifth. Okay, let's do a few more of these, because this is a weird rule. What about one like this? If I have 5m to the negative 3. And you look at this, and you say, I see a negative exponent, I gotta fix it. Well, who is this negative 3 applying to? Is it touching the 5? No, it's touching the m. The m is the base that has a negative exponent. And so remember, I can move it. Well, where is this right now? If you don't see a fraction, you know that means it's in the top of the fraction. You can always put a 1 on the bottom. And so this 5, what's this thing here? The m to the negative 3 will need to move. And so if I move it down, it will become m to the positive 3. Now the 5 does not have a negative exponent. It gets to stay put. Okay? Alright? Anytime you move a base and its exponent up or down or up, it just changes the sign of the exponent. Which leads us into our next rule. Okay? We've multiplied like bases. What if we divide like bases? And I can show you how this is related to a lot of things we've dealt with already. So let me give you an example. X to the 10th. Well, let's do well, that'll be okay. X to the 10th over x to the 3rd. the rule tells us that if I have a like base up top and a like base on the bottom, I can smush them together in the top. And what you'll do is you'll take the number from the top and subtract the exponent from the bottom. So 10 minus 3. So x to the 7th. Which this should make sense if we do a little bit of exploring here and list all these out. Let's see why this rule works. X to the 10 over x to the 3. What we end up with is 10x's on top of the fraction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's why I almost changed it to a smaller number. That's a lot of 10s, a lot of x's. And 3 on the bottom. Okay, all being multiplied. Well, an x on the bottom will eliminate or divide or cancel with an x from the top. So this x right here, it will, let's use a highlighter so it's just easier to see. It will cancel with an x from the top. And this x right here will cancel. So there's 3 x's on the bottom. They will cancel out 3 x's from the top. Okay? These 3 x's on the bottom will eliminate 3 x's from the top. So what are you left with? 1, 2, 3, 4, 5, 6, 7. I'm left with 7 x's in the top. Okay? Now, there's another way to show this one. I could move this x to the third up to the top with it, right? Now, if this confuses you, you can just not pay too much attention to it, but from the last rule we just had, if I move a base and its exponent up or down in the fraction, it changes this sign. So if I took this positive x to the positive 3 and moved it up with the other x, I would get x to the negative 3, right? Because moving this base up or down changes the sign. Now look what I have. I have 10 x's and negative 3 x's. That would be x to the 10 plus negative 3, which is the same thing as 10 minus 3, or x to the 7th. So you could just memorize the rule, but these are two kind of explorations of where the rule comes from. Okay? So, let's see. Let's do 2 more examples of these. So, I could give you something like this. What if I did something like this? P to the 3rd over P to the 7th. You see that? Well, what do I have here? I have like bases being divided, so I would combine them and take the top exponent minus the bottom exponent, 3 minus 7. Well, what is that? That's p to the negative 4. I'm not allowed to have a negative exponent. So I did my division rule. Now I gotta fix the negative 4. Well, this is understood to be on top of the fraction, so I need to move p to the negative 4 to the bottom to make it p to the positive 4. And once again, I can't leave the top naked. No shoes, no shirt, no service. You gotta put a shirt on it. So 1 over p to the 4th. Was there a faster way to think about this, though? Instead of skipping, or not skipping, but going through 2 different rules? Yeah, there kind of is. How many p's are up top? 3. How many p's are on the bottom? 7. There are more p's on the bottom, aren't they? And so 3 of these p's would cancel with 3 of these and leave me with 4 p's on the bottom. So I could have kind of logicked myself into jumping directly to this 1 over p to the 4th. Where there's 3 p's up top. You can kind of visualize this in your head. And there's 7 p's on the bottom. And you know that these 3 will cancel with 3 of those. And I'm left with 4 on the bottom. So that's why I like, where is it at? I like this visualization of the rule, where I could, in my head, I don't have to list out 10 x's and 3 x's, but I know that there's 3 on the bottom, there's 10 up top, and 3 of them are going to cancel with the other 3. And that leaves me with 7 up top. Same thing for this example. So it helps me do these division rules really quickly. You don't have to. It's fine to just follow the rules very methodically, and you'll never get them wrong if you're very careful with them. Let's do one more. Well, I don't know if you need another one, but one more just for good measure. X to the 5th over x to the 3rd. So if you look at this one, I got 5 x's up top, 3 x's on the bottom. The rule says to do 5 minus 3, which would be x squared. Okay, so I think we're good there. Alright, I'm going to hit you up with one more rule, and then we'll talk about scientific notation. Okay. I'll talk about next lesson in a second. And so this last rule is about how do we deal with parentheses. Okay, how do we deal when we have a lot of things inside here and an exponent on the outside? Okay, now this only works. Well, let's look at one thing at a time first. So here's how the rule is set up. And we can explore this one as well. X squared in parentheses raised to the 5th power. What would that be? What's the rule for dealing with exponents inside and outside of a parentheses? The rule tells us that this would just be x to the 2 times 5. That these two things get multiplied. And so that'd be x to the 10. Let's kind of explore to see if this makes sense. So let's look at the outside the parenthesis. It tells me I have 5. Well, what do I have 5 of? I have 5 of these sets of parentheses. So 1, 2, 3, 4, 5. And what goes inside the parentheses? X squareds. Okay. Now, looking at this, what is an x squared? An x squared is just an x times an x, right? So each of these is just 2 x's being multiplied. And if we're looking at multiplying all these things together, how many x's total do I have? That comes out x to the 10. Or you could say 5 groups of 2, that's 10. That's 2 times 5 or 5 times 2, right? So the rule tells us that I multiply. Exponents on the inside of the parentheses get multiplied by exponents on the outside. Now this rule only works, so let me give you an example and tell you it only works for multiple things like this if these bases are being multiplied or divided. If I put a plus sign in here, this rule does not work. Okay, I'll talk about this more in a second. Let's do some more of these examples. So how many bases do you see inside the parentheses? I see 2 separate bases. I see a 2 and an x. Now, what I like to do to follow this parenthesis rule really carefully is make sure all the bases have an exponent. Do you see 2 doesn't have an exponent? Well, what could I give it? Oh, well, if it doesn't show an exponent, it's understood to have an exponent of 1. So now I can easily follow the rule. Every base will get its exponent multiplied by the exponent on the outside. So that'll be 2 to the 1 times 3. And x to the 3 times 3. Which simplifies to, let's see, 2 to the 1 times 3. That's just 2 to the 3, right? And x to the, what's 3 times 3? That's 9. So there we go. Nice and simplified. We could do 2 to the 3rd. That's not too big of a number, is it? 2 to the 3rd is 8. We did that actually at the beginning of the lesson. I'm okay with either of these final 2 answers, though, okay? Either of these last 2 in blocks. Because all we're practicing are the exponent rules. Okay? So if I have more than one base in here, every exponent inside the parentheses gets multiplied by the exponent on the outside. So let's look at another example. How about this one? 4x to the 2nd power divided by y to the 3rd power, all in parentheses. And on the outside, let's do a 5. It doesn't really matter. A 5's good. Now, how many bases do you see inside the parentheses? I see a 4, I see an x, I see a y. So that means each one of them needs an exponent. This one has an exponent of 2. This one has an exponent of 3. This 4 does not have an exponent, so let's give it a 1. And now, I should be able to follow my exponent rule, which says that every exponent inside the parenthesis, the 1 here, will get multiplied by the 5. So 4 to the 1 times 5. The x has an exponent of 2, and that 2 will get multiplied by 5. And the y has an exponent of 3, and that 3 will get multiplied by the 5. And so let's see, that will be 4 to the 1 times 5 is 5, x to the 2 times 5 is 10, and y to the 3 times 5 is 15. Okay? So there we go. Now, notice I can do this rule if the bases are being multiplied or divided. This rule does not work. Does not work if there's a plus sign or a minus sign in there, like this, x plus 2 squared. It will not work if there's something being added inside the parentheses. So do not try to do it with that. Only with multiplications and divisions. Okay? Now, let me talk a little bit. I got one more thing to talk about, scientific notation. But before I talk about that, I do want to say, these are just all the exponent rules we will use that I've run through here. I ran through all these rules. And next lesson, I'm not really going to teach you anything brand new. We're just going to learn to combine them all together. So I can have a lot of things going on, and I can follow all these rules. And what's fun about these rules is ultimately they can happen in almost any order of operations. So a lot of times there's not a correct order to do these in. And sometimes you do them in different orders, and you will end up using different rules depending on which things cancel and which things don't. But you will get the same answer. So next class we will expand this ability. Okay? Now, let's look at scientific notation. Scientific notation is not something that's always in the course, but over the last few years, the lady that's in charge of it has really wanted us to put scientific notation in because the physical science and chemistry teachers and physics teachers come to us and say that the students don't know scientific notation. And so we say, okay, well, we'll throw it in with our exponents. Okay? So let's talk about what is scientific notation. All scientific notation is you have some number, some number, times 10 to some exponent, some other number, okay? So it could be something like this, 2 times 10 to the third power, okay? What this is a way to represent really large or really small numbers without having to, for instance, the number like this, 0.0000000000006, that's a really small number. I really would hate to have to try to figure out what this number is. But scientific notation gives us a really easy way to understand this number. We would write it in some way with some number here, how many ever places we have to move this decimal, okay? So I will teach you this, don't worry. I'm just introducing the need for it because it's hard to count all these. Or if I have a really large number, like say the lottery, I don't know what it is. Say the Powerball is $27 million. Well, that's a lot of zeros, right? 27 and then lots of zeros behind it. See, that's hundreds, thousands, millions, or say it's $27 trillion. It's never been that big. But anyway, just say it's really, really large. Hundreds, thousands, millions, billions, oh my, trillion, so say it's really a large number. Well, that's a lot of zeros to try to soak in. And so scientific notation will give us a way to write these really big or really small numbers using a one digit in front of a decimal times 10 to some exponent, okay? So here's how it works. Multiplying, so if you take any number, let's just do some experimenting. Any number, like 5, and I tell you to multiply it by 10, what's that going to be equal to? Just 50. It just added a 0 onto the end, right? What if I tell you to do 5 times 10 squared? Well, that's multiplying by 2 tens. That would just be adding 2 zeros onto the end. And I think you catch the pattern. 5 times 10 to the third, that would just be adding 3 zeros onto the end. And so I could do this as long as I wanted, all the way down, as big as I want. It doesn't matter. 10 to the 10. It would be 5 with 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so all we're doing is multiplying by a number of tens. Well, multiplying by a number of tens just makes the number bigger by throwing zeros on the end. That's the idea behind scientific notation. And so I want you to make this connection in your head. If I'm dealing with a really large number, when I do the scientific notation for it, the exponent will be positive. Okay? Because y'all know I'm dyslexic, and I had a hard time telling the positive and negative ones apart. And I would have to sit there and think about it and reason with it. It's really simple. If we're talking about a really large number, we're going to use a positive exponent. So then likewise, if I want to represent a really small number, so let's do the same kind of talk here. So if I do 5 times 10 to the negative 1, what that's going to do is put a decimal place in front of the 5. 5 times 10 to the negative 2, so that's 2 tens backwards. And so that would put another decimal place in front of the 5. 5 times 10 to the negative 3. That's going to put another decimal place in front of the 5. So it's how many decimal places we were moving. Okay? So if I did something like 5 times 10 to the negative 10, that would be 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then our 5. So if we're dealing with really small numbers, that's really a small number, we're going to think negative exponents, okay? Exponents will be negative. So all this exponent is telling us is how many places to move the decimal, either throwing zeros behind a number or decimal places as zeros in front of a number. Okay? So the only thing you need to know today is, can I write it in scientific notation and can I write it back as a normal number, or vice versa? It doesn't matter what order we do this in. So let's do some examples. You will get some questions like this on the test that you like to ask things like, okay, so I give you 2.7 times 10 to the 8. Could you expand that out? And the answer is yeah, we can. This is a positive exponent, so this is going to make a really large number. So what that means is I'm going to move the decimal 8 times. So positive exponent, that means this is going to be a big number, large number. And I'll move the exponent, or move the decimal, sorry, move decimal 8 times. Oops, I forgot the S. Times, because the exponent is 8. So let's move it 1 time, 2, 3, 4, 5, 6, 7, 8. Because it was right in front of the 7. It was right here, so I moved it 1, 2, 3, 4, 5, 6, 7, 8. So there's the number. See if I could put some commas to figure out what we're at. 270 million. Okay. Now, could I do one with a negative exponent? Like 1.3 times 10 to the negative 3. So you see, I see a negative exponent. So I'm going to think a really small number. And so let me do some scratch work for this one. And so how many places am I going to move the decimal? 3. But I need to make this a small number, so instead of, if I move it that way and added zeros, that would make a really large number. So it needs to move this way, 1 decimal place, 2 decimal place, 3 decimal place. That's where my new decimal goes, and I need to put zeros to hold these spots. So I'd get 0.0013. Okay, so I can take scientific notation and expand it back to the normal number system, or we could give you a number 1, 2, 3, 4, 5 and ask you, could you write this in scientific notation? So here's the rule for writing in scientific notation. You need to move the decimal so that you have one number in front of it. So let's see, 1, 2, 3, 4, 5, 6. So I have to move it 6 times to get 5.6. I have one number in front of the decimal. So I moved it 6 times. So that would be times 10 to the 6. Now, is this representing a big number or a small number? Well, look, it's a decimal with lots of zeros. That's a small number, so I need a negative. So 5.6 times 10 to the negative. I used to struggle with whether to tell me. People try to remember left to right, and then it's confusing whether you're converting it to scientific notation or from scientific notation. It's just easier to say, is it related to a tiny decimal or a really big number? Negative or positive? Way easier for my little tiny head. How about this one? So 5,900,000. Can I write that in scientific notation? Well, I'm going to need to move the decimal from right here. I need to move it. Let's see how many places I need to move it so that I have one number in front of the decimal. So 1, 2, 3, 4, 5, 6 to right there so that I have 5.9. So one number in front of the decimal. Times 10 to the, and how many times did I move it? I moved that one 6 as well. So is this going to be a negative or a positive 6? Well, is 5 million a big number or a tiny decimal? That's a big number, so this needs to be a positive 6. Okay? And so you need to make sure you're comfortable with converting one way or the other. Okay? Now, next lesson we will use this scientific notation to do some math. Okay? So hang tight. I know some of y'all are really bored with just seeing me do scientific notation, but we will use it in an interesting way next lesson. So you guys have an awesome day.